In this lecture, we will continue our attempt to grasp the essence of the invariant characteristic of curvature according to the remarkable or extraordinary theorem of Gauss, which says that the curvature is an invariant intrinsic characteristic of a surface, totally independent of the way that somebody thinks of the embedding of this surface in space. In this way, the curvature characterizes intrinsically a surface independently of space, and our method to abduct the truth of this theorem comes out of the tuning of an arbitrary surface through the notion of an osculating circle which is tangent at each point of the surface. It is rolling along and across this surface, giving eventually rise to the notion of the two principal curvatures, the product of which characterizes the intrinsic Gaussian curvature of an arbitrary surface, totally independently of how you embed this surface in space. It's interesting to point out, in relation to the sphere, which, as we have seen, has positive Gaussian curvature, as we explained in the previous lecture, that thinking in terms of our projective screen, our screen can be projective in two different ways, with respect to angle and with respect to area. And the fact that these two conceptions of the screen in relation to angle and area, they are not equivalent to each other, points out to the fact that the sphere is characterized intrinsically by some invariant, which is precisely the invariant of curvature. Now, the way that we were led to this notion of curvature is by considering, first of all, the conformal projection of the sphere, so the projection which is called stereographic and preserves oriented angles and, of course, circles, about which we think in terms of light. So this projection on our screen is obtained naturally through the bridge of light rays which enter into the sphere from the North Pole in this representation. The other, the Archimedean projection of the sphere, comes out of radially projecting the sphere on a cylinder and then unrolling the cylinder on a planar surface. This is also a projective screen, but this preserves the area of the sphere and not the angle. So the angles are badly distorted in this projection, whereas the area of the sphere is preserved under this projection. So in physical terms, if we think of the conformal projection of the sphere in terms of light, we think of the equiareal projection of the sphere, according to Archimedes, in terms of matter. In this way, we connect the notion of curvature out of the two distinct projections that we obtain in relation to the sphere with respect to light, the conformal projection, and with respect to matter in the case of the equiareal projection of Archimedes. We think of this in terms of matter because radially we project every point on the surface of the sphere on the cylinder. Of course, with the exception of these 2 points, the North and the South Pole. So in this case, the sphere is a matter sphere, and the matter which is distributed all around the sphere is projected in a way which preserves area, the area of distribution of this matter, onto a cylinder, which in turn is unrolled on a plane. In this way, the notion of curvature pertains also to the ratio or the proportionality between light and matter. This is something to keep in mind because the notion of curvature in physics is considered in relation to the distribution of matter, but in order to make sense of the curvature in relation to matter, we have to take into account the role of light as coming from the conformal projection. So it's a proportionality relation, or the ratio that you can make out of you projecting the sphere out of light in the conformal case and out of matter in the Archimedean case. And the universal method now to find the curvature through synchronization, so out of the natural communication scheme between the domain of harmonics and the domain of geometry, is using the method of osculating circles, initially conceived by Leibniz and used also by Euler and perfected by Gauss in order to give a quantitative measure of this invariant, the invariant of curvature of the surface. One more observation. You see that here we consider in this picture of the conformal projection that we consider light coming from the north pole of the sphere. So our screen is considered to be tangent to the south pole of the sphere. But of course, we could consider light coming the other way around. So we could consider that light is coming from the south pole of the sphere, and in this way our screen, on which we record the stereographic projection through light, is tangent to the north pole of the sphere. Now these two screens, they are not isomorphic to each other. In order to grasp the whole sphere, we need to be able to glue together these two spheres, these two projecting screens. So, in a way, the projection from the North Pole captures the upper hemisphere of the sphere, whereas the projection from the South Pole captures the lower hemisphere of the sphere. This can become obvious if we consider that the projection screen is transferred or is translated to the equator of the sphere. So at the equator of the sphere, we are able to glue together the conformal projections from the North Pole and the South Pole. Now, these two conformal projections are reciprocal to each other. So what we see in the projection through light from the North Pole is reciprocally related to what we see from the South Pole. This is important now in relation to the inside-outside relation that we have figured out from our discussion 2 lectures ago in relation to the inside-outside distinction from the perspective of the complex plane, depending on the center of synchronization. The center of synchronization is the point of the sphere where light comes from. So if light comes through the North Pole, then the center of synchronization is the center of this disk, which is topologically equivalent with the upper hemisphere of the sphere, whereas the other is considered as the outside. Now, if light comes from the South Pole of the sphere, these roles are reversed. So in essence, in order to consider the conformal projection of the whole sphere in relation to the both poles, we have to take into account, and this is a characteristic which pertains always to light, the inside-outside distinction, and then to glue these two projective screens together. And the gluing, which pertains to this inside-outside distinction, is the antipodal gluing, which we have called the analemma. Essentially, what you have topologically is a circle bounding a Möbius strip. So it has a non-trivial topological characteristic, meaning that it is non-orientable. So if we want to take into account, in terms of light, both conformal projections from both poles, we need to make the gluing at the equator, and the gluing of these two projections give rise to a non-orientable projective screen, which comes from the antipodal identification of these two disks. This is a characteristic which always appears in relation to light. After this observation, which clarifies also topologically what is at stake in the case of the conformal stereographic projection, we move again to the distinction of the three cases of intrinsic curvature. The first curvature, the first case, pertains to positive curvature, with the most characteristic is the case of the sphere obtained by tuning through rolling osculating circles. The second is the case of a plane which has zero Gaussian curvature, and the third that we want to discuss now in more detail is the case of a saddle surface, which is called the hyperbolic case of constant negative curvature. Now, the constancy comes from the fact that we will examine right now, is the role of the catenary. And the negative sign comes from the fact that the osculating circles, they have to be considered as directed. In this sense, the orientation has to be taken into account. And we see that in contrast to the case of a spherical surface, where the orientation is the same, in the case of a saddle hyperbolic surface, the orientations are opposite to each other, as it is obvious from this picture. Now, in this hyperbolic case, what is extremely interesting, and this is a qualifier of the notion of information that can be encoded in terms of a hyperbolic surface, again from the perspective of communication between harmonics and geometry, is the role of the catenary. So we have an intricate relation, and this is what will lead us to grasp the notion of a negative curvature. So we have an intricate relation between the catenary and the notion of an osculating circle. So this is what we will focus on now. Recall that the catenary is not considered again as a geometric operational object, but the catenary is considered again as a bridge between harmonics and geometry. The fact is that the catenary curve is the natural shape of a hanging chain under gravity. In this sense, we consider that gravity has the harmonic characteristics which give rise to this particular shape represented geometrically. Now, the issue here is that if we think of the catenary as a curve which is depicted on our screen, we can characterize it geometrically in terms of two things. The first is that at each point of the catenary, there is a tangent vector, which again will pertain to the notion of velocity or momentum at each point of the catenary. And also, there is, since our screen is based on the notion of orthogonality, there will be at each point a normal vector. So a vector which is perpendicular to the tangent at each point of the catenary. Now, with these two things, so the tangent and the normal, we have a complete geometric knowledge of the catenary. There is an interesting observation which points to the relation of the catenary with the notion of a space of negative curvature, a hyperbolic space. For this, we use the method of inversion. What inversion amounts in a geometric context? We said that the catenary curve is characterized at each point by the tangent and the normal. What happens if the roles of the tangent and the normal to the catenary are exchanged? This is the inversion. What happens is that if these roles are exchanged, we obtain another curve. This curve that you see here in this picture under the graph of the catenary. This curve has been studied by Huygens, and it's called the tractrix curve. The idea is that the catenary cannot be considered independently of the underlying tractrix on our screen. The characteristic now of inversion is that this curve here, the tractrix curve, which is related to the phenomenon of friction, to the physical phenomenon of friction. So here we have hanging chain, and here physically we have the phenomenon of friction, is the curve of friction. This curve here, if you see on our screen, has as tangents the normals of the catenary, and as normals it has the tangents of the catenary. So the role of tangent and normal is inverted as we go from the catenary to the tractrix. This is the geometric inversion. You see in the picture that if you consider from any point of the catenary the tangent, this tangent will be a normal to the tractrix, and inversely, if you consider any point of the tractrix and you take the tangent at this point, the tangent will be normal to the catenary curve. So the role of tangents and normals, they are inversed from the catenary to the tractrix. So this gives a kind of encoding and decoding that has to be considered simultaneously and synchronically in order to see how we go to the notion of a hyperbolic surface, so to negative curvature, from the perspective of the interplay between the catenary and the tractrix. Here is a picture which depicts the tractrix. What you will see here, and is the unique peculiar characteristic of this curve, that it is an equitangential curve. So the tangents at every point of the tractrix, or equivalently, the normals now, so the extension of this are normals to the catenary. Under the tractrix, they have all of them the same length. And this is the unique, peculiar characteristic of this curve. Now, how the tractrix is related with the notion of a hyperbolic space. Since we have a screen, the idea is that this screen can be rotated with respect to an axis. The rotation of the tractrix around this axis here gives rise to what is called the pseudosphere. And the pseudosphere is exactly the most characteristic instance of a hyperbolic surface which has negative Gaussian curvature. So here now we figure out how we go to the case of the hyperbolic pseudosphere, which should be considered as the analog of the sphere in the case of positive Gaussian curvature. We see how this is obtained through the catenary. So the steps again is that we consider gravitational field. Gravitation here pertains to matter, to the matter which constitutes the hanging chain, is the matter of the hanging chain. Under gravity, the chain gets this particular shape, the shape which is given by the arithmetic mean of two real exponential curves. As any curve on our screen, this is now a screen which records the shape of a hanging chain under gravity. So not in relation to light, but in relation to gravity. Is a matter chain. Geometrically, this is characterized at each point by the tangent, as usual, the velocity, and the normal, the perpendicular to the tangent. We invert the roles and we end up with the complementary curve of the catenary. And this curve is the tractrix. In this way, the hanging chain, the catenary, should be always considered together with its decoding geometric form, the form of the tractrix. And since this is a screen, rotation of the screen around this axis of symmetry here gives rise to the pseudosphere, which is the analog of the sphere in the case of positive Gaussian curvature. In this way, the pseudosphere is the characteristic instance emerging out of the rotation of the tractrix, so eventually out of the catenary curve, as the instance characterizing the spectrum of negative Gaussian curvature. An interesting observation now is the following. Recall that the Gaussian curvature is obtained by taking the product of the principal curvatures. So the osculating circles under rolling have a minimum and a maximal value. Now we will see why these values are equal to each other. This is what we will see straight on. And the second is that since the osculating circles are oriented in opposite ways, we have a product which is negative, but we have a negative square. Now, the idea is the following, that a negative square comes out of squaring something which is imaginary. Since the square of the imaginary unit gives -1. In this way, now, we can think of the pseudosphere of this hyperbolic surface as being a sphere which has imaginary radius. So the case of a negative Gaussian curvature can be grasped again from the case of a sphere, but a sphere which has imaginary radius. It seems from our previous lectures, what is on the imaginary axis is thought of in terms of synchronized velocities. A surface like the saddle here, or the most characteristic instance, this pseudosphere, it can be thought as a kind of a horn. Can be thought in terms of an imaginary radius. So it can be thought as a shape which comes from momentum space. Okay, since imaginary radius goes to synchronized velocities, and velocities on our screen bearing the complex numbers are always orthogonal to positions. So the imaginary radius of the pseudosphere can be thought most properly not in position space, but in momentum space, as the natural shape which is obtained from velocity. So it's a velocity space or a momentum space which bears the negative curvature. This is quite important because we have said that at least if we think in terms of quantum space, we cannot confuse position space and momentum space. These are independent, and we have to take both of them into account. There is an objective uncertainty which gives rise to quantum probability out of this interplay between position space and momentum space. Of course, all area in position space can be thought of, the characteristic explanation, which comes from the Pythagorean theorem, can be thought of as area which is swept out from velocities. But velocities should be always thought under the complex exponential function as being orthogonal to positions. So imaginary radius of a sphere in position space, which, as we said before, we think of it in terms of light, which comes through the North Pole or the South Pole, can be considered now in terms of matter through the imaginary tangent velocities as giving rise to the shape of the pseudosphere. So, in conclusion, what looks as a pseudosphere in position space is simply a sphere of velocities and in momentum space. So in momentum space, this pseudosphere bearing negative Gaussian curvature is simply a sphere which has imaginary radius. And imaginary radius is velocity under the complex exponential function. This is quite interesting because the conception of the pseudosphere now and every hyperbolic type of negative Gaussian curvature has been first pointed out by Lambert. It was Lambert who made this connection that you can think of the pseudosphere symmetrically with respect to the sphere as a sphere which has imaginary radius. But what was missing there is the fact that a sphere of imaginary radius should be properly thought of out of the communication between the harmonic and the geometric domain as a sphere in momentum space. So the analogy is that, as in the case of the Pythagorean theorem, we have the area of this annulus here seen in momentum space out of the harmonic parallel transport of all these tangents at the joint center of synchronization in terms of a disk, which is a disk of velocities, since the radius of this disk is made out of these tangents, which are all equal. In the same way, you can think of the pseudosphere in analogy to this disk of velocities. In this case, the pseudosphere is a sphere of velocities which have imaginary radius. In the same way, so metaphorically, as all these tangent velocities here in relation to a radius, they are orthogonal. So if the radius is real, then the velocity is imaginary, which boils down to what we know already from complex analysis, that in the domain opened up by the complex exponential function, differentiation amounts simply to orthogonality, which is given by the imaginary unit. This is the economy which is given and the simplicity which is given through the complex exponential function. We come back to see now how the pseudosphere can be thought of in terms of the tuning through the osculating circles. So the pi tuning, osculating circle of whatever radius is characterized by the same constant, the constant pi, the constant of Archimedes. What is changing under rolling the osculating circle is only the radius. You find the minimum and the maximal cases, you take the product, you invert this product, and then you find the invariant characteristic of curvature. So what we need to take here, since we work always with a screen, okay, this is always our setting. We work with a screen. We use now a screen to cut the pseudosphere, so to obtain a cross-section of the pseudosphere. If we do this, we get on our screen a cross-section which is precisely made out of a catenary curve coming together with its geometric complement coming from the inversion of the tangents and the normals, which, as we said before, is the tractrix curve. So this is obvious that this is a cross-section, since the pseudosphere has been obtained out of the rotation of the tractrix along this axis, this horizontal axis of symmetry. So a cross-section is giving rise on our screen to a catenary curve and to the corresponding tractrix. So a point on the pseudosphere in the cross-section will be a point on the tractrix curve on our screen, and it is this point Q that appears here. Now we have to relate, since we have in the cross-section these two curves, we have to relate this point, first of all, with respect to the length of this segment here, which is the tangent to the catenary, or equivalently, the normal to the tractrix, and this distance here, QR, which is the length from the point on the tractrix to the axis of symmetry of the pseudosphere. Now, this length here, we have to think in terms of the osculating circle, which makes the tuning on the pseudosphere. And it is immediate to see that this tangent to the catenary is the radius of the osculating circle in one direction, and this QR segment here is the radius of the other osculating circle, and rolling it around the pseudosphere in the other direction. And of course, it is immediate to see that these osculating circles are oppositely directed. It is this case that we have talked about here. But now it is clear from the picture that for every point, so for every variation of this point here on the tractrix, we have a relation between the length of QP and the length of QR. And these lengths now are reciprocally related to each other. So the length of QR is the reciprocal to the length of QP for every point of translation along the tractrix. And this observation now is what leads to the fact that the pseudosphere has a curvature which is of course negative, as we explained already, but it has a constant negative curvature, since the radius of the two osculating circles are, for every point of variation, reciprocally related to each other. So their product is constant and equal always to -1. In this way, the pseudosphere, or the sphere of imaginary curvature in velocity space, in momentum space, as the complete analog of the sphere in position space, is a surface of constant negative curvature -1, which is obtained through the tuning by osculating circles, the two cases, minimal and maximal, bearing, in this case, opposite orientation, and the fact that the radius of these osculating circles, they are reciprocally related for any point of variation along the tractrix. In this way, we see, first of all, how the pseudosphere is the complete analog of the sphere in two ways. The first, as a sphere of imaginary curvature, so as a sphere in momentum space, and secondly, as emerging out of a cross-section which records on our screen always a catenary together with its underlying tractrix. In this way, we understand immediately what is at stake here. I mean, the issue of negative Gaussian curvature in complete symmetry with the case of positive Gaussian curvature, also constant in this case, the case of the sphere, mediated by the case of zero Gaussian curvature, which makes what we call a flat or developable surface. It's a surface of zero Gaussian curvature. So the cases of positive and negative Gaussian curvature correspond symmetrically to a sphere which has real curvature, real radius, and a sphere which has imaginary radius. The curvature comes from squaring through the method of tuning by osculating circles, and in the case of the sphere, the curvature is positive, constant, and in the case of the pseudosphere, the curvature is negative, constant. But the case of the negative curvature, thought in terms of our screen, emerges out of this subtle relation pertaining to matter between the catenary curve and the tractrix curve. Having grasped now this relation, we can move one step forward to think of the notion of a catenary dome. The idea is that the pseudosphere now is obtained by rotation of the tractrix along this axis of symmetry. The question is, from the same screen, what we obtain if we rotate the catenary curve? The catenary curve can be rotated either in a convex way, giving rise to this geometric shape here, to this form, which is called a catenary dome. It is very well known in architecture, but can be rotated also in a concave way around this axis of symmetry, giving rise now to what is called a catenoid. The main interest now in the catenoid is the fact that it is a minimal area surface. A minimal area surface is characterized by the fact that it is enclosing the minimum of area in its extension. The catenoid in physics, it is the natural shape that you get out of a soap film. So if you consider two circles, the top circle and the bottom circle, and there is a soap film in between them, it will get the shape of the catenary because nature minimizes area. It is again an instance of the principle of least action. So from the same screen now, we have the information of the pseudosphere, but also the information pertaining to the catenary dome, so the rotation of the catenary in the convex way around, and the rotation of the catenary in a concave way, giving rise to the unique particular characteristic of what is called a minimal surface, the catenoid. Now, what is of interest here, in terms of curvature, it is the relation between the catenoid and the helicoid. Recall that the helicoid is the surface which is bounded by two helices, about which we have thought in terms of the universal covering of a circle on our screen, and gives basically substance to the notion of a quantum space. So there is a particular, very interesting relation between the catenoid and the helicoid, which is also a minimal surface. This is a higher order relation. And it's interesting to figure out what is this about. The fact is that all the distances along the catenoid are locally equal to all the corresponding distances along the helicoid. So the question is how we go from the catenoid to the helicoid. The issue is that the catenoid, because of the hole it bears in the middle, is non-simply connected. So it is topologically non-simply connected. It is multiply connected. In contrast with the helicoid, which is simply connected. Recall that the whole notion of a universal covering surface, the helix, is to unfold in a simply connected way the multiple connectivity of the circle. Now, this issue, in terms of curvature, appears in the relation between the catenoid and the helicoid. But the catenoid emerges not through the circle, but through the catenary. So there should be a deep relation now between the catenary, whose origin is the influence of gravity on matter, the hanging chain, and the helicoid, which comes out of the circle and eventually out of the sphere. Because we think of the conformal projection, so the projection of the helicoid on the underlying circle preserves all angles. So the natural bridge to think of it is in terms of light. So we have an intricate relation between matter and light in this setting, which says that the catenoid is locally isometric with the helicoid, but only locally. This is not possible globally because these two surfaces are not homeomorphic to each other. They are topologically distinct because exactly of the fact that the catenoid bears this hole in the middle. So it's multiply connected. Now the invariant characteristic of curvature, seen locally only, not globally, as in the cases that we have discussed already, of the sphere and the pseudosphere, brings up a relation now between the gravitational catenaries, so a relation to matter, and the light helicoids out of the conformal, so angle preserving projection of the helicoid on the underlying multiply connected circle, thought of as the equator of the sphere in the conformal projection. Recall that the understanding of the helicoid is, in our setting, intimately and intrinsically related with the conception of a helical standing wave if we bound any portion of the helicoid. So we have the phenomenon again of self-interference, which gives rise to this distinct quanta, the harmonics of this helical standing wave. But if we bound any portion of the helicoid, in terms of curvature, it becomes indistinguishable, so locally isometric with a catenoid. So from the perspective of two-dimensional space, so if you imagine beings having perception of two-dimensional space, the catenoid and the helicoid are locally only indistinguishable to each other. So the spectrum of distances locally along the catenoid and the helicoid, they are exactly the same. This points to a deep relation between the catenary now and the circle, between matter in relation to gravity and light, especially the conformal projection through the sphere. So the circle here is identified with the equatorial circle of the sphere, about which we have already talked about. This is a very deep theorem, and you can see that this is true only if you cut. So you cut the catenoid, and if you cut the catenoid, you can start unrolling it according to the helicoid. Now, the curvature is the invariant which makes these topologically distinct, inequivalent globally surfaces not only talk to each other, but having exactly the same local curvature. So locally, the catenoid as a minimal surface, by cutting and rotating, gives rise to the helicoid, so which unrolls in a simply connected way the non-simply connected catenoid. In this way, out of the natural communication between harmonics and geometry, went up in an invariant relation as pertaining to local curvature. So we can think of a local isometric deformation of the catenoid made out of the catenaries into the helicoid, which is simply connected and locally indistinguishable in terms of curvature with respect to the catenoid. This points to a deep relation between gravitating matter taking the free form of the catenary and light in a relation now to the conformal projection of the sphere, which bounds any piece of this helicoid, any local part of this helicoid, and such that The equator of the sphere is identified with a circle where this helicoid is conformally projected.